Today, the topic is federated learning with Flower, AI's next frontier. And I know that's quite a bold title, but I'm trying to live up to it. So let me start by actually giving a little bit of context on why we are doing this. I thought about how to structure this keynote, and I could dive very deep into federated learning and how it works and all the different algorithms that are out there. But I thought the much more important piece is to actually put it in context, frame why we should actually be interested in doing this, and what this will enable and how this will shape the next generation of AI systems. For doing that, you've probably all heard about the great discussion about GPU rich and GPU poor. And I think there's a nice analogy that can be made where we not talk about GPU rich and GPU poor, but actually the much more important question is data rich or data poor. And I think there's no better place to talk about this than PyData. So let me start by giving you, in quotes, the secret recipe for creating the next AI breakthrough. AI has evolved around three pillars, and they're model architecture, model size, compute, and data. So if you look at the model architecture, the breakthrough for deep learning was sort of AlexNet in 2012. AlexNet had 62 million parameters. Now, a much more recent model, Llama 2, has 70 billion parameters. It's quite a big difference. In terms of compute, AlexNet was trained on a GTX 580 or several GTX 580, which had 1.5 teraflops of FP32 performance. Comparing that to a much more recent H100 SXM, which has almost close to 2,000 teraflops of FP16 performance, which is what we're training these days. Huge difference, and it should be noted that models like Llama 2, they're not just trained on one of these GPUs, but literally on thousands or even tens of thousands of these GPUs. And then on the data pillar, we trained on ImageNet in 2012. What are we training on today? Actually, that's a topic that I would like to go into and show that this is actually this is the one pillar of these three that hasn't really evolved that much over the last decade. And there's a huge opportunity here. If we look at some of the recent AI milestones, we can see that they're all very, very data hungry. If we look at Llama 2, for example, Llama 2 was pre-trained on 2 trillion tokens. If we look at Whisper in 2022 by OpenAI, this was trained on 680,000 hours of speech data, so audio data, which roughly equals 77.6 years. Like someone sitting down and speaking for 77 years straight into a microphone without ever taking a nap. That's the amount of training data that went into training a competitive model here. And then last but not least, in reinforcement learning, OpenAI 5 in 2019 was trained on 45,000 years of DOTA self-play. So we can, it's pretty obvious here that those AI milestones, really the interesting models that push the boundaries of what's possible, they're very, very data hungry. So let's look at what kind of use cases, what kind of tasks could we consider to be data rich, and what kind of other tasks could we consider to be data poor. If we look at images that are of the style like images that you can find on the web, that I would classify as data rich. There's a ton of images on the web. You can find a ton of selfies, for example, on the web. But then if you look at image data in more specialized domains, for example, in healthcare, that I would consider data poor. So for example, it's easy to find a lot of images, a lot of holiday pictures, for example, on the web, but it's very difficult to find a lot of MRI scans on the web. Other examples, video, there's tons of video data on the web, but it's also quite generic. Again, if we look at specialized video domains like self-driving, for example, there are very few videos of a deer jumping in front of a car on a snowy, icy road going uphill on the internet. It's very difficult to find these. So companies that attempt to train on train models for self-driving, they need to sample these videos themselves. For text data, there's also a ton of text data on the web, but again, more specialized data, for example, text that coming from legal contracts is more specialized, and it's very difficult to come across on the web. So if you want to train a model for some kind of legal AI use case, it's difficult to do that with web scrape data, and you're again in a data poor domain. Speech data, there's a lot of speech data, especially covering the English language. If we look at languages other than English, speech data is much more rare, and for some languages very difficult to come across. So again, data poor domain. For reinforcement learning, you have tons of data in reinforcement learning when you do simulation and when you can run lots of simulations in a cheap fashion. Reinforcement learning in the real world is much more difficult, and again, we're in a data poor domain. And there's certain types of verticals and industries that could be considered data poor from that perspective. Healthcare, for example, medical AI researchers, they usually don't have access to tons of training data because this data is very valuable. And there are tons of regulations that prevent this data from being freely shared, being put on the internet. So it's difficult for them to train latest generation models because they're lacking meaningful amounts of training data. Similar situation in manufacturing, in finance, for example. If you look at, for example, fraudulent transactions in finance, these data points, they're very rare and they're locked down in data silos within in the individual financial institutions. And then automotive and personal computing are similar settings where some of the data can be collected, but a lot of the data actually that's out there and that would be very valuable for these models cannot be easily collected. Well, especially with yesterday's news, someone might say, well, but now we have Gemini. Gemini can do everything. Actually, here's an excerpt for the Google DeepMind Gemini tech report. And I'm quoting, "We find that data quality is critical to a highly performing model and believe that many interesting questions remain around finding the optimal dataset distribution for pre-training." So that's something they put in a tech report. There's unfortunately not a lot of information about the training set they used. Largely training data scraped from the web. But if we wanted to twist these words a little bit, even Gemini is sort of stating that if they had better training data, Gemini would probably be perform much better. So clearly, this is a challenge, but at the same time, we want to look at it as an opportunity. And we're in this interesting situation today where the data that is being used is actually just a small fraction of the data we have in the world. The data that is used for training is public and or centralized data. So it's either data scraped from the web or the limited amount of training data that a single institution, for example, a single research hospital, has internally. But there's actually much more data in the world. But this data is either sensitive, so you can't find it on the web, or it's distributed. It's distributed across different organizational silos. It's distributed across user devices. So it can't be used for AI training today. Why is that the case? We have all of this data, we want this data, we need it to train better models. So why can't we easily access it? Well, the classic machine learning approach is to move the training data to the computation. So in this diagram here, we can see a server in the middle, and then we can see some devices, but this could equally well be different institutions, for example, different hospitals that want to work together. We have this central server, and then before we can train a machine learning model, everyone needs to upload all of their data to the central server. So user devices, they need to disclose all the personally identifiable information. If we had hospitals clustered around this server, then hospitals would need to disclose patient data to the server. Well, actually, that's exactly where the problem lies. Just the pure fact that data needs to move, in many cases, in many industries, in many very valuable tasks, prevents us from accessing enough training data because the data cannot move. It's either that we have a lot of training data on the edge, for example, or that we have very sensitive training data, for example, credit card information or personal messages in encrypted chat apps that should not go to the server and where users expect this data to remain on device. Or we have regulations in place like a hospital needing to hold on to their patient data and needing to safeguard it. In other areas, like for example, finance, we also have strong regulations where even a single organization cannot centralize all of the data that they have. So they might have data in different regions, maybe data in the US, data in Europe, and data in Asia. But because of local regulations, they cannot centralize this training data even in their own infrastructure. Federated machine learning, federated learning, and federated evaluation just basically flips that. It says, okay, instead of moving the data to the computation, let's move the computation to the data. We're not going to collect data anymore. We'll leave the data where it is. The data doesn't have to move. And then we move the computation to where the data is, and we perform parts of the computation there. So we'll train the model locally on the local training data. And then instead of moving training data around, we just move models around. And with that, the data stays where it originates, and we can suddenly start to incorporate all of the data that is out there but currently not usable. We can suddenly incorporate it into our training workloads. So that makes this a same situation where in a classic machine learning approach that needs to move the data, we would be in a data poor environment, makes it suddenly a data rich environment because we can access all of this training data. How does it actually work under the hood? Let's go through a very basic, intuitive explanation, and then that should hopefully give you enough understanding of it so that we can look at the math behind it real quick and get a full understanding of how this works. So we'll start with a server, federated learning server, in this case, the Flower server. The Flower server initializes a model. So it's just a randomly initialized model. The model doesn't know anything about the task yet. And that model and the server has not seen any data. So there's not a single data point on the server. We then send the initialized model that doesn't know anything yet. We'll send this to the user devices, for example. Could be user devices, could be other types of data partitions, could be different hospitals. So we'll send the machine learning model to where the data is, to those, in this case, phones. And then each phone will train the model for a little while using the local data. So it has some local data that was collected through user interaction with the device. And it will use that data to train the model just for a little while, maybe one epoch, but definitely not until full convergence. So each of these devices trains the model for a little while, and each of these devices then ends up with a slightly improved model. So a model that knows a little bit more about the data. But each device, obviously, because each device has different training data, each device ends up with a different model update. So after that short training period on the device, each device sends the updated model back to the server. So we'll have the server, we have the previous model, and we have the new models that are coming back from those devices. Now what do we do with it? Well, the last step is we aggregate those models that we receive. We aggregate them into one new model, and a model that then hopefully has learned something about all of the data that is distributed on all of those devices. And after that, we just repeat. We repeat this process over and over again. So we have an aggregated model on the server. We'll again send it to those devices. Each device trains for a little while, sends the updated and slightly improved model back to the server, and the server aggregates them again. We are not running a full training on each device because that would make the individual models that are going back to the server too different from each other. And experiments have shown that approaches like this don't converge very well. So that's the reason why we only perform maybe a single epoch or 5 epochs on the local device, and why we repeat this process over and over again. With that, we should hopefully have the full enough of an intuitive understanding to look at the actual algorithm from the seminal paper on federated averaging. This approach is called federated averaging. The paper is called Communication Efficient Learning of Deep Networks from Decentralized Data. So there was a lot of emphasis back then on the communication aspects, but the same approach can be used in settings where communication efficiency is actually not that crucial. So if you walk through the algorithm step by step, we see the first part of it is what the server executes, and the second part of it is what the client executes. So what the server executes is before the loop, it initializes the model parameters, and then for a number of these rounds, it selects a random subset of clients that are out there. So this is especially important in settings where you have a large number of, for example, mobile devices participating in these workloads. Google, Apple, Meta, they have these systems in place, and they run workloads across sometimes hundreds of millions of devices. And then in such a setup, you don't want to run on all of these devices at the same time, but you want to select a small subset, maybe a few hundred, maybe in the low thousands, but definitely not more. So we select a subset. Let's say we select 200 clients. And then to each of those clients, we send the model parameters that the server has initialized. Each of these clients does the typical update like a regular centralized model training would do. So we have the local data partition. We split it into a number of batches, and then for each batch we perform SGD. And then after the local epoch, 1 epoch or maybe 5 epochs or something like that, we send the updated and hopefully improved model parameters back to the server. The server receives all of these, and then what it does to aggregate them in the very simplest form, it does a weighted average. The weighting happens based on the number of training examples on each device. So each participating device usually has a different number of training data examples, and based on that, we average the model parameters, and we get a new global updated model. And with that new globally updated model, we can then perform the next round of federated averaging. So again, we would select a subset of participating devices and go through the same procedure again. This algorithm is called federated averaging, often abbreviated as FED-AVG, and we'll see that later in code on how it works. Here's a small animation that once again visualizes the same approach. A data scientist initializes the model, model moves to the devices. Those devices, they are holding onto their local training data. They train the model, different models go back to the server, and the server aggregates them. And then we'll repeat this process. The same approach can be used for evaluation. In that case, it's called federated evaluation. So what we're doing is we already have a trained model, but we want to know how it performs. And this is often an often overlooked approach, I would say, but a very, very important one for certain domains. If you think about healthcare, for example, in healthcare, there's many startups that are trying to train better medical AI models, but it's we don't know how good those models are because they're so limited. We have limited amounts of evaluation data, and we don't have like an objective benchmark on how to compare different models that are supposed to do the same thing, on how to compare these to each other. So in this setting, there's an initiative called MedPerf, for example, and quite a few other initiatives that are trying to set up a federated network of data nodes where different hospitals contribute their data to allow others to evaluate their models. And by doing so, we will hopefully soon get to a critical mass of hospitals, each contributing their patient data. And then allow others to just evaluate their models. So no one has access to train on these models, but people can just, startups or larger pharmaceutical companies, if they have models, they can run them on this large federation of data nodes and then see and compare their models in an objective way to other models. One other related approach is federated analytics. In that case, what we're sending to these data partitions is actually not a model, but it's something closer to a SQL query, for example. And then we query the local data. For example, we could, again, sticking with the healthcare example, we could query different hospitals on the average age of people getting a certain disease. And then on the server side, we can aggregate these results together, and we'll get a much more comprehensive answer because the query has seen a lot more data, evaluation data. One thing I should add before we wrap up this section is, unfortunately, there's no free lunch. So federated learning, if you look at it through the perspective of privacy and security, can only be really private and secure with a careful, holistic design. So there's different things that need to be adjusted for. Usually, federated learning is not used in isolation. Federated learning is sort of just the enabling layer to access more data. But then other approaches, depending on the task and depending on the threat model, are layered on top of it. So differential privacy is a very important one. Another important one is secure aggregation. And these, again, depending on the threat model, depending on a carefully designed system architecture, should be used together with federated learning to make these systems secure and private by design. Let's go through a couple of examples, and then after those examples, I'll stop for a second, and I'm happy to take a couple of questions before we move on to an actual introduction into how this can be done in code. So federated learning examples, there's roughly speaking, there's two big categories of federated learning. One is cross-silo federated learning, which means training across different organizational silos. Popular example that we discussed at length now is healthcare, where also a big factor in healthcare is trustworthiness in machine learning. So in healthcare, again, we have the situation where different pharmaceutical companies or startups, they are releasing models or they offer models to, for example, look at MRI scans or other kinds of medical data. and try to see what kind of situation is there. So how can we achieve a situation where we can objectively compare all of those models? Well, federated evaluation is an important building block in that. And then after federated evaluation, how can we improve those models? The answer to that would be federated learning. Another important case is manufacturing. We have actually quite a few users and organizations we're working with in manufacturing. And they're facing the issue that each of these manufacturing plants, they're usually separate legal entities, and they're based around the globe in different regions. So it's very difficult for these companies, even if they own all of the subsidiaries, to centralize all of the training data. In addition to that, there's tons of training data within each of these manufacturing plants. So the sheer technical task of creating a system that centralizes all of this data is quite a difficult one. So in that case, organizations realize that it's much easier to just keep the data where it is and then to connect these different manufacturing plants for things like predictive maintenance, for example. So detecting faults before they actually happen. Another interesting one we touch upon is finance. So in finance, again, data is heavily regulated, and usually data, for example, that is generated in the US, it cannot be freely moved to other regions around the world, which is a good thing for customers, but for data scientists, it poses a challenge. So even if it's just a single bank that operates in multiple regions, these organizations are very interested in using federated learning because suddenly they can incorporate all of the data they have in different regions without violating any of the regulations that have been put in place there. The other big category of federated learning is called cross-device federated learning, which means training across different user devices. So imagine a single company that has maybe an application out there with a large number of users. Then those users are all generating data, but not all of the data can be and should be collected on the server side. Personal computing is obviously the big one. Incorporating, for example, very privacy-sensitive data into training workloads that sits on devices. Text models are a very good example. It's actually one of the very first federated learning use cases that has been publicized was to train the Android keyboard and then to train better prediction in the Android keyboard. So whenever you type a couple of characters, you get these predictions and suggestions for auto-completing what you were about to type. And the model that sits behind that, that model is trained using federated learning on a very large fleet of hundreds of millions of devices. Another one that doesn't immediately come to mind when thinking about cross-device federated learning is automotive. Actually, quite a few automotive companies are very interested in adopting this approach because, again, different local regulations force them to or prevent them from actually collecting data that is generated in the car just through the regular act of driving the car in different environments. There's actually very interesting data on those cars for automotive companies, but because of regulations, they cannot collect it. And some of the data they also should not collect it. If there's a camera that watches the passengers, whether maybe the driver is falling asleep, then that is data that should not be collected centrally. But obviously, such systems can be vastly improved through machine learning models. Okay, before we move on to Flower, maybe let's take a question or two, and then we can continue. Looking at the chat, does Flower use some type of heuristic to discover what type of training task to do, supervised, unsupervised reinforcement learning, when the model is moved to data locally, it is federated? Flower doesn't do that out of the box because Flower takes an agnostic perspective. So the perspective of Flower is to say, we want to provide generic infrastructure that enables you to build whatever task you're interested in on top of. So we're not prescribing a certain approach, and we're not doing this for the user, but we provide sort of a plugin architecture where users can choose the best approaches and then combine those to build whatever system, whatever is right for their particular use case. Okay. Looking at the Q&A section.
Put one on the screen if you want to take a look at that.
Oh, there's one on the screen. Give me a second. How would federated averaging work for tabular data? Wouldn't the concept limit the kind of algorithms you could use? Yes, that's true. So for different kinds of models, there's different kinds of aggregation algorithms. Federated averaging works still, after all these years, surprisingly well for models like neural networks. But then if you work with tabular data, a very popular approach on tabular data is to use, for example, XGBoost. And for XGBoost, there's different types of aggregation algorithms that aggregate those trees on the server side, and it also have customizations on the client side. So that's something that in the case of that frameworks like Flower, they usually build an abstraction that allows you to pick the right aggregation algorithm on the server side. So not every aggregation algorithm is compatible with every kind of model. Yeah, very good question. All right, in the interest of time, let's move on. So as you could see from the previous sections, there's a lot of moving of data and involvement of clients. Not moving of training data, but data related to model parameters. And for all of that, obviously, we need some kind of infrastructure. Our hypothesis is that these approaches are still too difficult to use for many, which is why we built infrastructure to make it a lot easier for people to take existing machine learning approaches and bring them into this new paradigm of federated learning. And this is essentially what we call Flower. This is the Flower open source framework. Flower is completely open source on GitHub. Everyone can install it, can use it, and can contribute to it. We actually have much more in terms of raw numbers. We have much more contributors from the community than the core team of maintainers itself. Flower's perspective is that the missing piece to take these approaches mainstream and to enabling more organizations to benefit and to creating a data-rich environment for themselves is that the infrastructure is still not where it should be. And that's why we're building Flower, and our perspective is that we need a unified approach for federated learning, federated analytics, evaluation that makes it very easy to bring existing projects into this new paradigm. And I'll show what this means in a second. On the right-hand side, this is something like a rough architecture diagram. You can see there's a Flower server. You can see there are different Flower clients connected to it, each with the model running. And those different clients, one thing that Flower that's a little bit unique about Flower is that it supports very, very different kinds of clients. So there could be everything from a laptop to a Linux server to a supercomputer, but then also much smaller devices like an Android phone, an iOS phone, and maybe even a car connected to the very same server, running and participating in the very same workload. And in order to do that, we need to do quite a few things. We need to support Android and iOS, Python, cross-silo, cross-device, horizontal, vertical, differential privacy, secure aggregation, secure multi-party computation. And we need to support all of these paradigms in a simulation setting where users can simulate this, and also operations to really fully deploy these systems. And we try to build one solution that allows you to do all of that, but only learn the stack once. So the Flower ecosystem, in order to do that, allows you to integrate with all the tools you know and love. We support pretty much every machine learning framework out there, and a lot of other popular tools like weights and biases, for example, to log your examples. Another big aspect that I just briefly touch upon is this idea of taking a single solution, a single framework to move from development all the way to deployment. And in federated learning, that's a bit more complex than in some other stacks. So we support development on a single machine. Then you can move this first prototype, for example, you can move this onto a larger compute cluster to simulate a large number of devices. You can also simulate the same thing on a real device cluster. If you're targeting mobile devices, for example, that's quite an important aspect of it. And then later on, you can use the very same code base and project to deploy it to a large fleet of devices. Simulation performance is something we put a lot of effort in. What you can see on this chart is how many, the total number of clients that are in a client pool, and then also how many of these clients you can run concurrently in the simulation. Those numbers are quite old, but you can see that compared to what research settings usually look at, Flower is in a completely different ballpark. There's a lot of research that went into the design and engineering of the framework. I'm not going to list all of the papers, but here's a rough architecture diagram that sort of shows the layered architecture where on the client side, you have the regular training pipeline and the client-side data, which is very similar to centralized machine learning. But then on the server side, we have this concept of a strategy that sort of allows you to, gives you sort of a plugin architecture for aggregation algorithms, also for how to configure those individual clients for training, which clients to select, and makes these things, these components isolated and very easy to build and contribute to, and also customize, obviously. Flower is a large community. This is something we're quite excited about because we get tons of contributions. People are building a lot on top of it, and the feedback we get from that mainly drives the roadmap that we have for Flower. In terms of numbers, I think it's very safe to say that developers love Flower. We have 100 contributors, more than 100 actually. We have more than 1,000 projects on GitHub that depend on Flower. So this is always projects where someone else published their own project, which depends on Flower. We have 2,800, more than that, developers on the Flower Slack, and we have more than 3.3K stars on GitHub. And as you can see here in this plot, this is GitHub stars plotted on a globe. What we quite love about this is that we're not just present in the usual tech hubs around the world, but really we have this global community that is coming together to build this. We'd appreciate a star on GitHub. So the GitHub URL is github.com/adap/flower. I believe it's also, I also added this to the resources here on AirMeet. And then now it's already time to go into a live demo. Let me stop sharing my screen for a second and then bring up the live demo. Okay, you should be able to see my full screen now. And I'm just going to walk through a project. This is a simple federated learning project with PyTorch and Flower. And as you will see, most of the code is just a regular PyTorch sort of hello world project. And then there's very little code needed to take this existing project and federate it using Flower. So what we can see here is we're starting with the client side because that's where the actual model training happens. What we can see here is, first of all, a number of imports. And then what follows is just a regular PyTorch training pipeline. So the NN module, the training function, a test function, and a data loader. We're starting with the NN module. The NN module, this is just a very simple convolutional neural network with a number of fully connected layers. This is, we did not author this originally. This is actually just a simple CNN adapted from the PyTorch, the tutorial. We then have a training function, also a very simple one. The training function, what takes the neural network itself, it takes a training loader and the number of epochs that should be trained. And then similar to that, we also have a test or evaluation function, which just takes the neural network and a test data loader, and then does the evaluation. And then last but definitely not least, we have a load data function. We are using a library here called Flower Datasets. This is a library we released fairly recently, which can be used to easily partition existing datasets. So if you wanted to simulate a federated system, you would usually go ahead and take an existing dataset like C410 and then partition it into multiple chunks, so that you can use each of these chunks to simulate different data on different clients. And in that case, we are doing just that. We're taking C410 and we're partitioning it into 3 partitions. So that's there to simulate 3 clients. And to determine which one to load, we pass a node ID here. We could also call this a client ID. That's the regular PyTorch training pipeline. So we could put this all together in a main function and then call the training and evaluate after training. Now we move on to the federated part of it. So a little bit of just admin code here. We enable, when we start the script, we add a --node-id, so we can pass in which data partition to load, and then after that we create an instance of our model and we load the data for this particular node ID. And now comes the small part of code that's actually needed to federate this model. And the federated part of it is we are wrapping this existing training pipeline. We're just wrapping this in what we call a Flower client. So Flower offers this convenient convenience class called NumPy client to make it easy to federate pipelines that are compatible with NumPy. And what we do for that is I'm going to discuss the last 2 functions first. We're going to have a fit function, fit method, and an evaluate method. So the fit method, when the client runs, it receives the parameters that are coming from the server. So the current, the latest version of the global model. And it receives a configuration that can be used to tell the client, for example, how many epochs to train. What we do then is first we call set parameters, which causes the local model to be updated. So the local model still has old parameters. We just received a fresh set of parameters from the server. So we're updating the local model. After that, we call a train function. We pass the updated model and the train loader that has the local training data. This trains the model. And then after the training, we again extract the updated model parameters, so the slightly improved model. And we are also returning the number of local batches used or local training examples to the server to do the weighted averaging. And then evaluation works in the same way. We update the local model, we run the test function, and we instead of the updated model parameters, we return the loss and we also return the accuracy to the server. And then to start the whole thing, it's just one function, start client. We tell it the address of the server so it can connect to the server. And we create an instance of client and pass this to start client. That's the client side. The server side could be as little as a single line of code. I added a little bit more to make it more obvious what's going on. So to the server, we pass this strategy. In this case, we're using fed averaging. but there's quite a few other strategies. So if I just open the autocomplete here, you can see FedYogi, FedProx, FedAdagrad, a lot of others, and those are just the ones that start with Fed. There's also XGBoost based ones, because we had this question earlier. And then we could easily switch to a different strategy here. And I also have this function to aggregate this custom metric, the accuracy on the server side. Going into the actual code, we can see 4 terminal windows now. On the top, this will be our server. Let's start the server, which is just Python server.py. And then we have 3 more windows, which are there to simulate 3 clients. So let's start the first client, Python client.py, and then node ID 0. So that client is now starting up. It's connecting to the server. We are starting the second client with the node ID 1. And as soon as it's running, it receives a training task. The server is waiting for the second client to connect because it is configured that way. You could also tell the server to wait for at least 3 clients or at least 500 clients before it starts the training. And then we see these multiple rounds. So we see the first round of training, we see the first round of evaluation, we see another round of training. And then after the whole thing is finished, we can see that the distributed loss is going down, and we can see that the accuracy is going up from 14% to 18 to 21 in that case. Not very good, just 3 rounds, and probably not optimal hyperparameters, but just to showcase how this works. Now let's tell the server to wait for at least 3 clients. Let's change that. Let's start the server again. Let's start the first client. Let's start the second client. And then we wait for a second, and we see that nothing happens. Because we configured the strategy in a different way, we set min available clients is 3. This causes the strategy to wait until at least 3 clients are there. So let's start third client now, and then the training should commence. And we can see that it's starting to run, and we'll see a similar situation as we saw before. That concludes the live demo. I'll stop sharing that part of the screen now, and I'll go back to my slides. If you're interested in diving deeper, there's obviously a lot more to learn. There's a full tutorial on flower.dev. Just on the landing page, there's a big button, take the tutorial. And now I would like to wrap up and leave quite a bit of time for questions by talking just a little bit and very briefly about future directions. So our vision and the reason why we're working on this infrastructure and why we're working on Flower and the whole ecosystem around Flower is that we want to see important industries like healthcare. We want to see these industries to become data-rich environments. We want the breakthroughs that we are seeing in other domains where we already have data-rich environments. We want these breakthroughs to become available. We want healthcare, for example, to be transformed through the ways that AI gives us these days. And in order to achieve that, we need to have infrastructure that allows us to turn these different domains into data-rich environments. Same can be said for manufacturing. Same can be said for finance. Finance is, for example, a very interesting one where we see fraudulent transactions. Each financial institution needs to try to find fraudulent interactions to prevent crime on a global scale. And only through better machine learning models we can better detect those fraudulent transactions. And we can only get to better machine learning models if we again turn the finance domain into a data-rich domain. Same can be said for personal computing. No one wants their personal data to be disclosed and potentially on a server that could be hacked and data could be leaked. So if we can bring those advances of machine learning to the domain of personal computing, but keep data private, then every single one of us will benefit from that. Same can be said for automotive. We all want safer cars and less traffic and less accidents. And in order to achieve that, many of these things can be achieved by just building better models that detect if a driver is sleepy, that detect dangerous situations, and that prevent cars from crashing into each other. Last but definitely not least, I want to say, if this is interesting to you, we just announced a number of positions and we are actively hiring. So if you're interested in that, check out careers.flower.dev. And our next community event is coming up, Flower Summit in 2024. Dates will be announced pretty soon. It will happen in March, either in person in London or online with a live stream. And that's a wrap. I hope this was interesting to you, and I'm very happy to take questions now.
Awesome. Thank you so much, Daniel. We have a bunch of questions. Let me put some questions on stage. First one.
I'm going to read out the question. To distribute training across silos, you would need to assure that the data has the same format. How are you dealing with this in federated learning? Great question and important one. That's absolutely true that we need data of the same shape, same format. The way you can do this is in Flower, in particular, that's the framework I know best. You have a lot of flexibility on the client side. So I've just the way I started the client was sort of the hello world way of doing it, where you have the very same code running on each client. But then what you can also do is you can customize this on a per organization or per silo basis. So you could, for example, customize the data loading and then transform the data from its original format into a common shared format. Another way that to do this, which is probably a bit more common, is to just locally have some kind of transformation layer that runs every once in a while and that outputs the original data in a common shared format. And then everywhere, every single node that participates in such a federation can run the exact same code because we have the exact same data format. But the big advantage, obviously, is that all of these organizations that are participating, they can keep the data in its original format in their original systems. They don't need to change anything about their systems. It's just an additional add-on layer that sort of pulls the data, transforms it, and then makes it available to the federation in a unified format.
Awesome. Thank you. Let me get on the next question.
Do you plan Flower to be like a marketplace where data owners can offer their data assets for training? This is something that has been, this idea has been sort of floated a couple of times to us. Right now, Flower is only an open source framework, and you can use the open source framework. You can contact us to help you if you want to deploy these systems. But as of today, you still have to run Flower yourselves. We'll probably at some point, because there is quite a bit of demand for it, also offer hosted solutions to make this easier. But a data marketplace, I would say, is something, it's a very interesting idea. And I think there could be some potential in it, but it's something that's definitely years off. And the demand that we see for these kinds of systems is in a different area. I think right now a lot of individual organizations are exploring this because they can deploy it very quickly and solve their own problems. And then I think in the long run, this could become more of a thing as organizations get more familiar with the idea of federated systems, Maybe they've deployed some federated systems internally across different regions, for example, if it's a multinational organization. And as they become familiar with this kind of system architecture, they will, I think, become also this idea of data marketplaces, where still everyone has full control over their data and what happens to their data, I think is a very powerful one. But it's not something that will, I guess, happen in the next 6 months or so. For security, is any code sent from server to clients or just parameters are sent? Great question. This is something that is configurable. So and this depends a lot on the kind of system you're running and the kind of requirements you have. So security obviously is of utmost importance. And in situations where the client does not trust the server fully, there's no need, or there's a way to configure the client to just run with the code that it has locally, and there's no way for the server to send any code to the client to just execute. And that's a very important property. That's very important to make this possible. That's actually in Flower, that's the default. And the default is the client would never execute any code that is coming from the server. That being said, in some environments, it's actually wanted that the client can execute code coming from the server. So imagine a situation where there's a single organization that's in control of all the different data nodes, and it just wants to deploy a pilot system and just experiment a lot with and learn how these workloads are behaving. So in that case, it can actually be very beneficial to allow dynamic code execution on the client. It's not the secure way to run such a system, but for prototyping and explorative projects, it can be quite beneficial. And in such cases, this will be possible.